Good morning, everybody. You are welcome to the International Conference on Science and Technology Research. I'm Adeolu Julius Alawode of the Department of Petroleum Engineering, University of Ibadan, Nigeria. And my co-authors are Alawode, B.O. Rishamika, and I. Muritala. I'm here this morning to present the findings of research work titled Investigating Oil Recovery Potential of Aluminium, Oxide, and Nanoparticles after water and surfactant flooding of a Nigerian reservoir core sample. The outline comprises of background to the study, statement of problem, literature review, materials and methods, results and discussion, conclusion and background to the study. After primary recovery, that is after using the natural energy of the reservoir to produce oil, the use of water flooding, and immiscible gas injection for fluid displacement, and the use of water injection for pressure maintenance are termed as secondary recovery. And about a third of the original oil in place can only be recovered through traditional primary and secondary recovery methods. More production from existing oil field could be achieved through enhanced oil recovery, and traditional EOR methods are chemical flooding, gas injection, thermal processes, and microbial EOR. Nanofield flooding was introduced because of nanoparticles' ability to alter reservoir conditions and migrate through pore troughs to improve microscopic displacement of oil. Nanofield is a colloidal mixture consisting of nanoparticles dispersed in a fluid to improve the desired properties of. Now, statement of problem. Traditional EOR methods are costly, hence the industry is looking for cheaper methods of enhancing oil recovery, though microbial EOR methods is the cheapest. It is not favorable in high temperature, high salinity, and deeper reservoirs condition. Also, a major drawback in microbial EOR method is low corrosion. Nanoparticles, as I said at the time, have abilities to alter reservoir conditions. Hence, the contributions of nanoparticles in different EOR modes should be investigated for the Niger Delta reservoirs. Literature review. The experimental research work on nanofluid EOR was surveyed and presented as shown here, starting with Kanch et al. 2009, Oyeko and Ogoro 2010, down to Omotosho et al. 2019 and Oyemachi et al. 2020. Also, as part of the literature review, the review works on nanofluid EOR were surveyed, and this starts with Kong and Owade 2010, Ayatollah and Zarafat 2012, down to Lee et al. 2018 and Agista et al. 2018. Now, materials and method. Materials used are cylindrical core samples, crude oil sample, brine, treating X100 surfactant, and aluminum oxide nanoparticles. Methods comprise of determination of density, specific gravity, API gravity and viscosity of the crude oil. API gravity is evaluated as 141.5 for specific gravity minus 131.5. And kinematic viscosity is determined by Oxford viscometer and evaluated as effluent time times viscometer constant, while the dynamic viscosity is evaluated as kinematic viscosity times density. Also, the scanning electron microscope analysis of nanoparticles were carried out, and crude oil interfacial tension IFT was determined using a tensiometer. Also, determination of total porosity and grain density of the core sample was carried out using a computerized ultra-pore porosimeter, where appropriate billets and core sample were put inside the microscope to determine the total porosity and grain volume and density of the sample via the software of the porosimeter. Core flooding starts with primary brine flooding. Here, the dry core sample was flooded with brine by a positive displacement pump at a flow rate of 48 cm3 per hour. An effective core porosity was determined as effective core pore volume over core bulk volume. Also, the absolute permeability of the core sample to water at 100% water saturation was calculated using Darcy's law. K equals Q mu L over A delta P, where the symbols or parameters have their usual connotations. Drainage is the process of displacing a wetting phase with a non-wetting phase. Therefore, drainage consists of using oil to displace water in the core sample. Flooding continued as only water was produced during oil breakthrough with water during water and oil production, but was stopped when only oil was being produced at irreducible water saturation. Also, the endpoint permeability to oil at irreducible water saturation was evaluated using Darcy's law. Then, imbibition commenced. Imbibition is the process of displacing a non-wetting phase with a wetting phase. Here, water is used to displace oil in the core. Flooding continued as only oil was produced during water breakthrough with oil and during oil and water production. Imbibition also continued by determining by evaluating the volume of oil and water produced and delta P across the core, with the aim of determining the effective permeability to water and effective permeability to oil over a range of water saturation. Respective relative permeability to oil and water were also determined to plot the relative permeability curve. However, it is more appropriate to use endpoint permeability at irreducible water saturation than using the absolute permeability when we obtain water saturation 100%. This is so because the endpoint permeability to oil at irreducible water saturation represents the flow condition just prior to commencement of water flooding. Recovery factor of water flooding is water flood oil recovery divided by original oil in place times 100. And pore volume was also of the injected water was also determined. Surfactant flooding commenced after water flooding, and here the respective volume of surfactant with water and oil produced were measured. Surfactant flooding was stopped when residual oil saturation was attained, that is, when only surfactant was produced, and the recovery factor was determined as surfactant flooding oil recovery divided by original oil in place times 100. Also, the pore volume of injected surfactant was determined. After surfactant flooding, nanofluid flooding commenced, and nanoflooding was stopped when residual oil saturation was attained, that is, when only nanofluid was produced. The recovery factor for nanofluid flooding is nanofluid flooding oil recovery divided by original oil in place times 100. Also, the pore volume of injected nanofluid was determined as shown. Result and discussion. Properties of core sample, crude oil sample, and brine sample are as shown here. Table 1 shows dimensions, porosity, and grain density of core samples, while Table 2 shows the property of crude oil and brine sample at room temperature 20 degrees Celsius. Also, the photomicrograph showing the nanoparticles textural and morphological structure is shown here. Figure 1 is of 1500 magnification, while Figure 2 is of 500 magnification. The nanoscale explains the ability of the nanoparticle in migrating through pore trough to actualize remarkable oil recovery. Also, the crude oil interfacial tension were measured, and here it is observed that the crude oil interfacial tension reduction at the crude oil surfactant interface was more pronounced than at the crude oil brine interface. This is due to the synergy of surfactant in reducing IFT. Also, the result for primary brine flooding shows that the effective copper volume is 23.12 cm3, and pressure drop across the core is 0.197 psig, while the permeability, absolute permeability to water at water saturation of 100% was evaluated at 639 millidarcy. Oil flooding shows initial oil in place of 17.36 cm3, and pressure drop across the core is 0.734 psig. Water flooding shows oil produced as 9.05 cm3 and residual saturation as 8.31 cm3. And also, the endpoint permeability to water at residual saturation is 201 millidarcy. Table 4 shows the variation of the effective water permeabilities with water saturation. 4 shows the plot of effective water permeability with water saturation, while Table 5 shows the variation of relative permeabilities to water and to oil with water saturation using the absolute permeability to water at 100% saturation of water, that is 63 MD as base case. It is observed here that as the relative permeability and effective permeability to oil is reducing, the relative permeability and effective permeability to water is increasing. It should be noted that KRW plus KR is less than 1 at the start of water flooding because the absolute permeability at 100% water saturation is used as base case here. However, it's also noted that the KRW plus KRO is less than 1 because of the different viscosity, mobilities, and wettability potentials of oil and water. Table C and Figure 6 shows the variation of relative permeability to water and relative permeability to oil with water saturation using the endpoint permeability to oil at irreducible water saturation, that is 26 millidarcy as base permeability. Here, it is observed that KRW plus KRO is equal to 1 at the start of the flood because endpoint permeability to oil at irreducible water saturation is used and is considered more appropriate. Surfactant flooding shows oil produced of 1.01 centimeter cube, and the volume of water and surfactant produced is 9.94 centimeter cube. Nanofluid flooding, for 10% nanofluid flooding, oil produced is 1.1 centimeter cube. For 20%, oil produced is 0.5. For 40%, the nanofluid flooding incremental oil recovery is 1.15%, and for 60% nanofluid 60% weight nanofluid flooding, there is no incremental oil produced after injection. The variation of injected fluid oil produced and recovery factor is shown here in table. Also, the plot of volume of oil produced versus volume of injected fluids are shown in Figure 7, Figure 8. Plot of oil recovery versus volume of injected fluid shown in Figure 9. This shows the incremental contribution of nanofluid flooding after the potentials of water flooding and surfactant flooding have been exhausted. Conclusions and recommendations. In this work, nanofluid of 10% weight and particle concentration yielded a higher recovery than that exhibited by surfactants. This is attributed to the ability of nanoparticles to migrate through pore troughs and travel long distance in porous media to yield remarkable microscopic displacement of oil. Significant incremental oil recovery by nanofluid flooding is therefore established in this work to be achievable after the potentials of water flooding and surfactant flooding are exhausted. To expand the frontier of knowledge, investigating the potential of different nanoparticles, nanomaterials, and biomaterials for oil recovery is recommended. Thank you for listening, and have a good day.